All right, good afternoon, guys. So let's get started. Today we'll do AC circuits. Okay. Now, before we get into this, let me show you a simple thing about DC circuits. So here's a battery. Here's a resistor, and this is the load. Okay. So what you're interested in is what is the current in the circuit. Okay. And from Ohm's law, you know that the current is the EMF divided by the resistance. Okay. So so just keep this in mind. This is the load. We will generalize this term to something called impedance. Okay, so we'll apply this to AC sources. This is a DC source. It drives a current in this direction. That's the positive terminal. Okay, it drives current only in one direction. We'll replace this by an AC source. Okay, and that's what you get out of your wall. Okay, and we'll be interested in connecting a general circuit here. Okay, and we'll be interested in the current that's coming out of the circuit, the current that the source is delivering. Okay, so we'll keep coming back to this, but so we're looking at AC circuits. You guys know what AC stands for? Oh, alternating current. Okay. All right. So here's how. Here's an AC generator, AC voltage generator. So here's a wire that's connected to these brushes, these rings, and these brushes that touch the rings connect to the outside. Okay. So if you turn this wire, the magnetic flux through this wire is changing, and an EMF is induced in this coil. And that EMF looks like that. And this is an AC voltage. Okay. So how do you turn this wire? So in a windmill, the wind is turning the blades, which is turning this wire. In a dam, the flowing water is turning this wire. In a coal power plant, you burn coal, produce steam, and the steam is turning this. In a nuclear power plant, you split nuclei, produce steam, which is turning this wire. Okay? So whatever energy you're inputting, that's turned into electrical energy. Okay, so that's how you're doing this. Okay. Now, so you're getting an AC signal here. And it turns out that the angular frequency of this signal is equal to the angular frequency at which this thing is rotating. Okay? All right, so this is how you get an AC signal. Okay? This is the electrical symbol for an AC source. Okay, so when you see a source like this, so you saw that this is a DC source. This is an AC source. Okay, and the voltage it provides is that. Okay, so there's the amplitude of the voltage, and it's a sinusoidal voltage. That's what we'll look at. Okay, so now this is the goal of the chapter. Okay, we'll connect an AC source. Here is your circuit. Okay, and what you want to know is what is the current that is being delivered to the load, to your circuit. Okay, so here's the AC source. Here's the amplitude of the voltage. There's the frequency, angular frequency of the voltage. Okay, and what you want to know is what is the functional form of the current. And here's the current. Okay, now this current, the amplitude of the current is related to the amplitude of the voltage. So it's E max divided by Z. Okay, just like current amplitude in a DC circuit is, the current is EMF divided by the resistance. We're going to generalize that. So the current being delivered to this circuit is the voltage amplitude divided by Z. That'll be the impedance of the circuit. Okay? So Z is the generalization of resistance, and it's called impedance. So there's the amplitude of the current, and then sine omega t minus phi. Okay. Look at this. So here's the voltage. Okay, this is the phase factor of the voltage, and here's the phase of the current, and you see the current is not in phase with the voltage. So what this is saying is sometimes the voltage might be rising, but the current would be decreasing. Okay? So there are two things that we are interested in an AC circuit. What is the impedance of the circuit, and what is the phase factor? Okay, so in all of the chapters, in the rest of the chapter, those are the two things we'll be interested in. Okay? Now this phase factor is between pi by 2 and minus pi by 2. What you learn is, so let's make sure we understand this. Okay. So here's your load. Okay. Here's the circuit, here's the load. And, well, you want the load to do something. You want the load to cook your pizza, for instance. Or if this is a washing machine, you want it to wash your clothes and stuff like that. What you learn is, if for this circuit, if the phase is either pi by 2 or minus pi by 2, this is not cooking anything. Okay? So when the phase factor is 90 degrees, all you're doing is delivering energy half cycle, and that energy is given right back. So what you learn is, when maximum power is transferred to the circuit, phi is 0. Okay? All right, so let me step back a second. So here's what we want to do in this AC circuit. You're connecting an AC source to the load. The two things that you're interested about this circuit is, what is its impedance? What is the impedance? What is its total resistance? And then what is the phase factor of the circuit? Okay. Again, when this phase factor is 0, that's when maximum load power is transferred to the load. If the phase factor is either pi by 2 or minus pi by 2, no work is being done here. Okay? So in our AC circuit, we are interested in these two guys. All right, so now that we know our goal, let's start off with the simplest element connected to your AC source. So we're going to connect a resistor to the AC source. Okay. All right, so let me do this. So we have an AC source, and the voltage is E max sine omega t. And then I will draw our load as a black box. Okay, so for our circuits, we are interested in finding Z and phi. Okay. All right. right, so for the first black box, what we're going to do is we're just going to connect a resistor. Okay, so the simplest possible element. Okay, so we're going to connect a resistor to our AC source. Okay, so for this source, it turns out that, okay, again, we get all our results by applying Kirchhoff's loop rule. So if you, for this loop, if you go around the loop, the net voltage around the loop is 0. Okay, so for instance, ET minus ITR should equal 0. Okay, and so from this equation, you'll get this. Here is the functional form of I. IT is Vmax over R times sine omega t. Okay, so here's your expression for the current, and compare this to our general form, or Vmax Vmax over Z sine omega t minus phi. Okay, so the two things we're interested in is Z and phi. If you compare this, Z is equal to R. And what is phi? 0. So for this element, Z equal to R, which makes sense. It's just the resistor, and phi is 0. Okay. All right, so now let's connect different elements. Okay, again, we started off by saying when phi is 0, that's when maximum cooking happens. Okay, so when you connect a resistor to an AC source, maximum power is being transferred. Okay, so what you want is when you use capacitors and inductors, you want the load to behave like a pure resistor, and we'll see how we do that. Okay. All right. Now, so here's the current. The current is sinusoidal. Okay. So here's the current. The instantaneous power being transferred to the load is I square R. I is that. Okay, so it's time dependent, and here's I square. Okay, and that actually, so the frequency that you get out of the wall is 60 hertz. So you have 120 peaks, like that. So if you have a bulb, one of those incandescent bulbs at home, that bulb is shining, it's flickering 120 times a second. Okay, so why don't you see the bulb flicker? That's what this means. Okay, your bulb is flickering 120 times a second. Why don't you see the bulb flicker? So anything that flickers more than 30 times a second, your vision persists. That's how TVs and all work. On a TV, it's a still image that's being drawn. If they draw it more than 30 times a second, then it appears as a continuous smooth motion. Okay? So anyway, but the bulb is flickering 120 times a second. Okay? So since your eyes can't perceive that, all we are interested in is the average power. Okay? So if you take the time integral of that, okay, so here's power, okay, and you take the time integral of that, and this is how you would calculate the average power. So this would be I max square R sine square omega t 0 to t dt, and omega is 2 pi f, so there is the period. Okay. So if you take the average over one period, this integral, no, 1 over t, this guy is 1/2. Okay. All right, so let's go back to our DC circuit. The power delivered here is I square R. The power delivered to the load is I square R. All right, so the power delivered to this circuit, and the power delivered to this load is I max square R divided by 2. Do you guys see this? This and this guy, it's I square R. This factor of 2 is annoying. So this formula is different. So what we do is, to make this look just like that, all we'll do is we'll define something called IRMS. IRMS is I max divided by root 2. And now this expression looks exactly like the one for the DC. Okay? And this RMS stands for root mean square. So the root mean square is, so just like the name suggests, root mean square. So so for a sinusoidally varying quantity, you take the square of it, mean, calculate the average value, there's the average value, okay? And take the square root of that, and that's what you get. So in AC circuits, we'll define RMS values so that your expressions look like DC expressions in DC circuits. Okay? All right, so for this element, again, what we're doing is we're connecting an AC source to a circuit. And what we want is, for this load, we want to know two things, Z and phi. So for a pure resistor, Z is equal to R and phi equal to 0. Okay? So those are the two things we wanted to know, and there it is. Yeah? And we've also defined RMS values. So IRMS is that. So let's say here's a vector, there's an angle. What is the y component of the vector? A sine theta. Okay. So look at this. The value, and the voltage as a function of time is V max times sine of theta. Okay, so it looks like it's the y component of a vector. Similarly, the current is I max times sine theta. It looks like the y value of a vector. Okay. So what we define is, we define so these are the vectors. These are called phasors. Okay, and we make the phasor rotate counterclockwise at that frequency, at angular velocity omega. Okay, and the instantaneous value is the y component of this vector. Okay, what you're doing is you're learning a technique which will help you get around solving differential equations. Okay, again, so here's a AC source that you connected to this circuit. Okay, so ultimately what you'll be interested in is finding the current through each element. And to solve that current, you'll use Kirchhoff's laws, but you will end up having to solve differential equations. Okay? Now to get around that, you're learning this technique, the phasor technique. All right, so here are the vectors. Here's the voltage vector and here's the current vector, and these vectors are rotating counterclockwise at omega t. And the instantaneous value is just the y component of these phasors. Okay? So a phasor rotates counterclockwise at the same frequency as the associated as that associated with the variable. Okay. So you'll see an example of this in a second. All right, so we'll connect our next element. Here's a inductor connected to our AC source. Okay? And again, using Kirchhoff's rules, we'll apply the loop rule. If you go around the loop, the net voltage around the sum of all the voltages around the loop should be 0. So if you go across this, there's the voltage across the source. And then the voltage across this is minus L di by dt. Okay? So to solve for this current, so again, what are you interested in? The current in this circuit, the current that's being drawn through this thing. You have to solve this differential equation. Now this guy is easy, okay? So here is the voltage, okay, Vmax, and here's the current, okay? So going back to this, so here's the voltage, and here's the current. What is it that we are interested in? We are interested in Z and phi. All right, let's compare that to this equation. Okay, so IT is Vmax over Z sine omega t minus phi. Okay, so if you compare this, you see Z, the resistance of this element is omega L. Okay? And actually we give it a special name. We call it XL. So Z equal to XL equal to omega L. So what are we saying? The resistance of this element in an AC circuit is given by omega L. Look at that, it's frequency dependent. Okay. So the frequency of the signal coming out of this wall is 60 hertz. The resistance of this guy is frequency dependent. As the frequency increases, the resistance linearly increases. Okay. You double the frequency, its resistance doubles. How about this guy? Does its resistance change with frequency? Z equal to R. It's frequency independent. So this guy doesn't care if the AC voltage switches back and forth. The resistance is not frequency dependent. But for this guy, the resistance impedance is frequency dependent. Okay? So higher the frequency, higher the impedance. Okay? And the phase shift is pi by 2. Okay? So Z is equal to omega L, and the phase shift is pi by 2. Okay, those were the two elements that you wanted to find. Okay, for any given load, and there they are. Okay. And you can see that, here's the voltage, here's the phase of the voltage, and here's the phase of the current. And what this is saying is the current is not in lockstep with the voltage when an impedance is connected. When an inductor is connected. So here's a diagram, okay? So you can see that here's the voltage, and here is the current, okay? So in this part, the voltage is decreasing and the current is rising, okay? Here the voltage is decreasing, and again the current is still rising. Here in this part of the curve, the voltage is decreasing and the current is decreasing as well. But you see, voltage and current are not in lockstep. And here's the phasor diagram. So here's the voltage vector, and here's the current vector, and that thing is rotating. And the instantaneous voltage is the y component of that, and the instantaneous current is the y component of the current, at any instant. All right, so again, reactance or impedance is the generalized term. So the inductive reactance is omega L. Okay, so the reactance is frequency dependent. Very important. And the current lags the voltage by 90 degrees. So the third element we'll connect is a capacitor. Okay. And here is the voltage, AC voltage that we'll apply. Okay. And again, the Kirchhoff's rule says that around the loop, the sum of the voltages around the loop should be 0. So let's start here. This is Vmax sine omega t. And then the voltage across this is, the voltage across a capacitor is Q times Q over C equal to 0. Okay. So Q T is C Vmax sine omega t. Okay. QT is that, and then you take the time derivative of that and you get the current in the circuit. Okay. So IT is this guy. All right, let's compare this to the general expression that we have. It's Vmax divided by Z sine omega t minus phi. Okay, so if you compare these two expressions, you see that Z is 1 over omega C. Okay, so what we are saying is the resistance, the impedance of this guy is 1 over omega C. So as the frequency increases, the resistance of this guy decreases. And phi is minus pi by 2. So the phase shift is minus pi by 2. All right, so let me review this stuff again. All right, so what we are interested in is the following. We're going to connect an AC source. We're going to connect an AC source to our circuit. What we are interested in, what is our load, what current is being delivered to our load. Okay. And so IT will be E max, the amplitude of the voltage, divided by Z sine omega t minus phi. Okay. So these are the two quantities we wanted to find for our load. For a simple resistor, Z is equal to R and phi is 0. For an inductor, Z is omega L, phi is pi by 2. Yeah. For a capacitor, Z is 1 over omega C, and phi is minus pi by 2. Yeah. So those are the three basic elements. Okay, so for a capacitor, the impedance is 1 over omega C. Again, the reactance of a capacitor decreases with frequency. Okay, so capacitive reactance decreases with frequency. And the current is 90 degrees ahead of the voltage phase. So the current is leading the voltage. Okay. So the current is 90 degrees ahead of the voltage phasor. Okay. and they're rotating counterclockwise. All right, so now that you've learned how the simple elements behave, we'll do the next complicated thing. Okay, so we'll connect them in series, all three elements. Okay, so here's our new load. We're connecting the AC source to that. And again, we want this. Okay, so we want to know two things. We want to know the phase, and Imax is really Vmax. So IT is Vmax over Z sine omega t minus phi. Okay. So we would want to solve that. Okay. Now to solve for the current, what you could do is you could set up a differential equation, and let me show you. Okay, so again, we'll use Kirchhoff's loop rule. Okay, this is Vmax sine omega t. And then when you go across the resistor, it's minus IT over times R. When you go across the inductor, it's minus L di by dt. And when you go across the capacitor, it's minus Qt by C. And that's equal to 0. And Q is, so IT is dq by dt. Okay, so this is really, so this is dq by dt, and this is d square q by dt squared. So this is a second order differential equation that you would have to solve. Okay, you would solve for qt, you would solve for qt, and then get it from there. Okay. All right, so that's how you would solve for this, but you've learned the phasor technique. So you will avoid solving this differential equation. Okay, let me write down the second order differential equation. Okay, so there's the second order differential equation that models the behavior of this circuit. Okay. All right, so instead of doing that, we'll use our phasor technique. Okay, so this is the voltage amplitude across the resistor, this is the voltage amplitude across the inductor, and this is the voltage amplitude across the capacitor. Okay, so let's say this is the phasor current. So that's the amplitude of the current in the circuit. The voltage phasor is in phase with this. The voltage across the inductor is ahead of the current, and the voltage across the capacitor is lagging the current. So, and the amplitude of the voltage across the three elements, the amplitude of the voltage across the three elements is the vector sum of these guys. So it's this vector plus this vector plus this vector. And so the y component is the voltage across the inductor minus the voltage across the capacitor, and the x component is the voltage across the resistor. So there's the amplitude of there's the instantaneous voltage across these three elements. Okay. And there's the current. The current is, so in this setup, it's phi, the current lags the voltage by phi. And these phasors are rotating. Okay. So you can either solve this differential equation or use this phasor technique to solve the problem. Okay. And so the amplitude of the voltage, or the instantaneous voltage, is VR square plus VL minus VC square. Okay, and this is Imax R times Imax XL minus I max XC. Okay. And I max is common, so you pull that out, and V max is I max times this, and that is your Z. So that's your Z. So that's one of the things we were interested in. Remember, for this load, you're interested in what is the total resistance of this load, or total impedance of this load, and that's the total impedance of that load. Okay. So the impedance of the load is R square XL minus XC square and square root of that. The other thing you're interested in is phi. Okay. Phi is, remember, phi is this, the phase factor. So we found the impedance of that circuit. Now we want to know what is the phase factor. And so the phase factor is given by, this is the phase factor, it's tan inverse of XL minus XC over R. So this angle is equal to tan inverse of this quantity. All right, so for this circuit, for a series RLC circuit, we know Z and phi. Okay. Now you guys understand that you can do all different kinds of combinations. So you could do this combination, for instance, and that's a totally different circuit. Okay, and you would find you would want to know IT and so on. You would want to know what is Z and phi for this circuit, and so on. And we are not doing that. Okay. So, but that would be the idea. So here's another circuit. This is a parallel combination. And again, you would want to know Z and phi. Okay, so that's your goal for all circuits. So for this simple combination, for a series combination, and that's one of the more important applications, Z is given by that, and there is phi. Okay. All right, so what this table shows you is the following, and this stuff is important enough where they put that in a table. So here's your black box. Here's the load. When the load is a pure resistor, what are we interested in? We are interested in two things, Z and phi. For a pure resistor, Z is equal to R, there is the impedance, and phi is 0. When this is a pure capacitor, Z is equal to XC. What is XC? XC is equal to 1 over omega C. Okay. And phi is minus pi by 2. When the load is a pure inductor, Z is equal to XL, which is equal to omega L. Yeah. And phi is plus 90, plus pi by 2. If this load was a combination of a resistor and a capacitor, Z would be equal to that, and phi would be between minus pi by 2 and 0 degrees. Yeah. If it was a pure resistor and an inductor, this would be Z, and phi would be between 0 and pi by 2. When you have a series combination, there is Z, and phi would be negative if XC is greater than XL. It would be positive if XC is less than XL. Okay. So again, like I said, this stuff is important enough where they put it in a table. Okay, so here's an AC source, and here's your load, and those are the two things you're interested in. Okay. So now let's make sure we understand this. This is sort of the punchline. Okay, so you've connected a source. Okay, and this source is driving this current. Okay, So again, the source is V max sine omega t, and the current being driven is V max over Z sine omega t minus phi. Okay. So the power being delivered to your circuit, is your circuit cooking anything, is the question. You guys understand? All right, so let's say you put a pizza in here. Will your pizza be cooked? All right, so the power being delivered is I, the instantaneous value of the current, times V. So there is I, and there is V. All right, so what you do is you take the time average of that. So that's the instantaneous power, and here's how you take the time average. Okay, so you integrate that over one time period. Okay, if you integrate this, here's what you get. I max, V max divided by 2 times cosine phi. There, that factor. That guy is the important guy. What happens if phi is pi by 2? That's 0. If phi is pi by 2, there's no power being delivered there. Your pizza will never cook. So if your load is a purely capacitive or a purely inductive load, phi is either minus pi by 2 or pi by 2. So if you connect a pure capacitor and an inductor to an AC circuit, nothing gets cooked. When is maximum power transfer happening? When phi is 0. For a purely resistive circuit, that's when the maximum cooking happens. Okay? All right, well, why do we care about this? So for instance, okay, so the way our infrastructure is laid out, you have large power plants remotely located, and then you transmit power to a city like that. Okay? This guy, these wires have inductance to them, the transmission wires. They have a non-zero XL. Okay? So what do cities do? They have to add capacitors at the end before the power comes into the city. So you add XC, so that gets canceled, and phi is 0. And phi becomes 0, so maximum power can be delivered to the city. Okay? All right. So power capacitors are used to balance the impedance of the effective inductance of transmission lines. So you guys have all seen these outside your cities, wherever. So that's what they're doing. Okay. So the bank of capacitors, their goal is to make phi 0. So maximum power is delivered to the city. Okay. All right, so you have quality factors. Okay. The quality factor tells you how sensitive to frequency the load is. Okay. So you see, this is the power delivered to the load, and as a function of frequency. So at this frequency, XC is equal to XL, and maximum power is delivered. Okay, so at omega naught, XL equal to XC. The circuit is purely resistive, and maximum power is delivered. Okay. And if you increase frequency, so XL, remember XL is equal to omega L, and XC is equal to 1 over omega C. Okay. So when you increase the frequency, XL increases, XC decreases, and so this becomes an inductive circuit. When you decrease the frequency, it becomes a capacitive circuit. And you see, when you move away from a purely resistive circuit, the power delivered decreases, okay? And the question is, how fast, how sensitive to frequency is your circuit, okay? And this is measured by the quality factor. So the quality factor is at what frequency is the maximum power delivered divided by what frequency shift you have for the power to go to half its maximum value. Okay? So smaller this thing is, more sensitive it is to frequency. Okay? And this is relevant for tuners. Okay, so instead of an AC source, now you're getting energy from an electromagnetic wave. Okay? And your circuit is being, you want to all right, so when you want to catch a station, there are nearby stations, and if the nearby stations, okay, so this is the station you want to catch, and if your circuit was not sensitive enough and this nearby station gave you transferred that much power to your circuit, you'll get disturbance. Okay? And if your peak was sharp and the nearby station only delivered this much power, then you'll get a very clear signal. Okay? So your tuner will be good. So what you want is in a tuning circuit, you want a very sharp peak, okay, and a very high quality factor. All right, you learned about transformers, so our infrastructure is an AC infrastructure because right now the way we've set up, we have large power plants and then we get power, we have to transport power over a long distance. And you can minimize transmission losses with an AC infrastructure. Yeah. If you had a DC infrastructure, you would lose more power in transmission. Okay. Now in the future, in 50 years from now, when you have more local production, when everybody has solar panels on their roofs, you could be either DC or AC because you don't have to worry about power transmission. Yeah. All right, so here's a transformer. So you saw that your transformers only work with AC sources. Okay? So you attach an AC source and the magnetic field switches back and forth, which induces a voltage here. So the voltage in the secondary coil is N2, the number of turns in the secondary coil, divided by N1, the number of turns in the primary coil, times the amplitude of the voltage in the primary coil. So if N2 is greater than N1, it's called a step-up transformer because V2 is greater than V1. If N2 is less than N1, then V2 is less than V1. So that's a step-down transformer. Okay. So in this transmission, here's a step-up transformer. So N2 is greater than N1. And here are step-down transformers. Okay. Step-down transformers outside the city, and these are the things that are sticking up on the poles near your house. Okay, another step-down transformer. Okay. Yeah. For long distances, power is transmitted at around 800,000 volts. Okay, so we'll talk about a couple of circuit elements. Okay, so the voltage coming out of the wall is an AC voltage, okay? And here's an AC voltage. So Your laptop, for instance, doesn't work on that. It likes a DC voltage. Okay. So the question is, how do you convert this to a DC voltage? Okay. So here is a device called a diode, and the diode is sort of like a gate. It only drives a current when this end is positive. If this end is negative, it doesn't drive a current, so it's an open circuit. Okay. So let's say you connect this, and during the positive cycle, it'll drive a current. During the negative cycle, it's an open circuit, it becomes. So the positive cycle currents are passed through. But you threw this money out the window, the negative cycles. So you want to fix that. And you can fix that by using 4 diodes. If you connect 4 diodes like this and connect an AC source, what you'll see is on the load, you'll see all the 4 cycles, the positive and the negative cycle. Okay. So when this is positive, the current goes through here. It won't flow through here. It'll flow through here, flow like that. During the negative cycle, it'll flow through here. It won't flow through here. It'll negative cycle flow through here, and then right. Okay. So now you've captured both the waveforms. Okay, but your laptop doesn't like this. It likes a smooth, flat voltage. So how do we fix that? Then if you connect a capacitor parallel to that, that'll smooth out this curve to something like that. Okay. So that box that you get with your laptop, that's what is in there. Okay, so you plug when you connect do you have a charger? Anybody have a charger? Huh? Yeah, or any charger, yeah. Or your phone charger. Okay, so that box, that thing has this stuff in it. That's what's in there. Of course, with a lot more enhancements, but that's basically what it is. Yeah. So the brick that Apple sells you is that. Okay. All right, so we'll briefly mention filters. Okay. Nowadays, if you have a wire, you want to maximize the use of wire, and what you do is you have carrier signals. You'll have low frequency carriers and high frequency carriers, okay? And then your information rides on this thing, okay? So if you have a signal here on this low frequency and a signal on the high frequency, how do you separate these is the question. Okay? So what you do is, okay, you're sending a signal, combined signal down here, okay? And when you hit a capacitor, remember the capacitor has an impedance of omega C. Okay, so for high frequencies, this is essentially, the resistance is 0, so this is essentially a short circuit. Okay, so you won't see any voltage across it. So if you have all kinds of signals being carried, high frequencies are not seen here. For low frequencies, the impedance is high and low frequencies are seen. So the output you only see the low frequencies. High frequencies are not seen. So this is a low pass filter. Okay, it passes low frequencies. Okay, so again, what you're getting is a mixed signal, and all you're seeing is low frequencies here. Okay. And that's what this graph is telling you. don't use these nowadays, but back in the old days and during your parents' generation, uh, the phone company would send down the wire using their wires. They would send internet signals and telephone signals on the same wire. Okay, so you remember that? All right. What's that?
I've heard about that.
All right.
That, like, you can't,
What?
the internet would be messed up if you get like a phone call.
Right, right. So your filters weren't working properly. Okay. But internet connection operates at a high frequency. So the carrier signal for the internet data was a high frequency, and for voice signal it was a low frequency. Okay. So you have a mixture of signal coming, and across the capacitor is you get this low frequency signal out. Okay. And yeah. So this was the device. This was a low pass filter. Okay. A high pass filter is a filter that lets through high frequencies. Okay. So again, at high frequencies, this is essentially short. At low frequency, this is a very large resistance, and it doesn't let through low frequency signals. And you can see the high frequency signals across the resistor. Okay. So here are two filter devices. Okay. And again, why do we need this kind of stuff? Why do we need this kind of filters, these kinds of filters?
Separate the two types of frequency provided by our system.
Well, if you can separate it, now on a given wire, you can send multiple signals, low frequency carriers and high frequency carrier signals. Okay. So a single wire can carry multiple messages. All right, guys, so that finishes this chapter.